Okay, so let's see theorem about embeddings of the solid phase. If S is greater than n over 2 plus k, then Hs of Rn is continuously embedded in ck infinity. Okay, so this is the space of functions with k continuous derivatives vanishing at infinity. In other words, if f is in Hs of Rn and S is greater than n over 2 plus k, then after possible modification of f in a measure 0, f is in ck infinity. Okay, infinity. And as it is a continuous embedding, we will have that the norm of ck is less than equal than the norm of, well, solid space S2. Okay, so this will let us relate the weak derivatives with derivatives in the classical sense. Okay, so let's prove this in the case, first in the case k is equal to 0, and that means that s is greater than n over 2. Okay, okay, so first we show that if f is in Hs of Rn, then f transform is in L1 Rn. Okay, so we have the norm 1 of f transform dxi. Okay, so this will be equal to, okay, so what we have here, but now we multiply and divide by this factor, um, 1 plus xi squared s over 2. Okay, and so now using Cauchy-Schwarz inequality and separating, let's say, this from this, we will have that this is less than equal than lambda SF. Recall the definition of the norm of the Sobolev, and multiply. Okay, what has to be left? Okay, the xi, well, 1 plus xi squared s, 1.5, both on norm 2, and this will be less than equal than a constant that depends of s, and multiply by the norm of f s2. So if s is greater than n over 2, then we will have that the norm infinity will be equal to f transform and transform, and now we know that this is less than equal than uh, f transform norm 1. Okay, this is infinity, and well, what we know now is that this is less than equal than cs f and the norm of Sobolev. Okay, so so we have what we were looking for, k equal 0. We can use the same argument for k greater than or equal than 1 if f is in Hs of Rn, and now with s greater than n over 2 plus k, okay, then for alpha in um, yeah, positive integer n, well, recall what we define as a, the sum of all the components, and less than equal than k, then it follows that the x alpha f transform is in L1, and well, we have that and the norm dx alpha f infinity, okay, um, is less than equal. Okay, so again we have the derivative of the transform, but norm 1, this is one of the first theorems that we saw, and well, then if we transform this, we know that this it is 2 pi I xi, this is all to the alpha, and f transform, okay, this is norm 1, and this will be less than equal, for the same reason as before, then cs f s2, okay. Okay, so now a corollary. If s is equal now than equal n over 2 plus k plus theta, with theta in the open interval 0, 1, okay, then hs Rn is continuously embedded in ck plus theta Rn. This is the space of ck functions with partial derivatives of order k held continuous in theta. Okay, so held continuous, it's like a Lipschitz condition, but the difference, well, if you recall Lipschitz, you have a constant here, and this absolute value, but when we consider held continuous, we will have theta in this exponent. Okay, so if a function is continuous differentiable, will also be Lipschitz continuous, and Lipschitz continuous will be Hilda continuous, okay, and the Hilda continuous will be uniformly continuous, and finally continuous, okay. Okay, so another theorem, embedding theorem, if S is in the open interval 0 n over 2, then Hs of Rn is continuously embedded in LP Rn, and now P is equal to 2n over n minus 2s, okay, or let's say s is equal n 1 over 2 minus 1 over p, okay. So moreover, for f in hs for n, we'll have that the norm of f p less than equal than a constant that depends on n and s, norm ds, I will define now ds, 2 less than equal than a constant, and now the Sobolev norm is 2, where d, let's say lf is equal to minus Laplacian 1/2 f, okay, and this will be equal to 2 pi psi absolute value, let's say L, F transform, anti-transform. Okay, I'm sorry, this is an L. Okay, now yes. So this is the definition of D of S or DRL. Okay, it doesn't differ from what we've been saying of the Sobolev of the definition of um, the Laplacian with a exponent. So you can prove this inequality using like we did before, considering that this is a function uh, transform and then anti-transform. But let's see how to prove this other um, inequality. Okay, so we want to see this inequality, the norm of fp is less than equal than a constant that depends on finiteness of the norm 2 of dsf. So we define ds of f equal to g, okay, or let's say f is equal to d to the minus s g, okay, and so let's say that this is equal to a constant multiplied by 1 over xi absolute value s g transform anti-transform. Okay, so this taking into account the definition of ds. Okay, now put in a negative exponent and the constant that remains. Okay, so if you transform this function and transform the multiplication, then you will have that this is equal to the constant over x to the n minus s convolution g. Okay, so now putting the norm of fp will be equal than f is d to the minus sg, so this is the norm of d minus sgp, and this will be equal to this norm, the norm of this cns over x n minus s convolution g. Okay, and so recall this as the kernel of the reserve potential. So we can say that if this is the risk potential, we can use the Hardy-Littlewood Sobolev inequality to bound this, and we can bound it by CNS and norm of G2. Okay, so by definition of G, we will have that this is equal to ds f2. Okay, this is what we wanted to see. So if S is in this interval, Hs is continuously embedded in LP. Okay, but if we consider an F in L2 such that its transform is 1 over, for example, 1 plus psi and log 2 plus xi, you can prove that F is in H and 2 exactly, so it's not here, and you can see that F is not in L1 of Rn, but well, so if it is not in L1, F is not in L infinity of Rn. Okay, because you can see that F naught is equal to uh, the integral of F transform. This will be equal to infinity. Okay.